In this video we will understand diffusion models. We will go through a Python notebook to see how to train a model from scratch. Eventually we will see how text prompting can be combined with diffusion model to generate new content. Let's first of all introduce the diffusion models. Diffusion models are generative models which have been gaining significant popularity in the past several years. They are currently used by DALL-E 2, OpenAI's image generation, and other platforms. The goal of diffusion models is to learn a diffusion process that generates a probability distribution for a given dataset from which we can then sample new images. In the case of computer vision, diffusion models can be applied to a variety of tasks, including image denoising, in-painting, super-resolution, and image generation. This typically involves training a neural network to sequentially denoise images blurred with Gaussian noise. The key elements of diffusion models are forward diffusion process, reverse diffusion process, training, sampling. Let's analyze these concepts one by one. The forward diffusion process is a Markov process where at each step, a small amount of Gaussian noise is added to the data. The goal is to map the original data distribution to a simple, tractable distribution, typically Gaussian noise. This process can be mathematically represented by the reported expression, where xt is the data at step t, beta t is the noise variance schedule, and n denotes a normal distribution. The reverse diffusion process aims to invert the forward process. Starting from the noise, the model attempts to iteratively denoise the data, reversing the steps taken in the forward diffusion process. This is done by learning a parameterized model that can predict the mean and variance of the distribution of xt-1 given xt. Training a diffusion model involves learning a neural network to reverse a gradual noise process applied to data. The model is trained to predict and remove the noise at each step, allowing it to generate new data samples by reversing the diffusion process starting from random noise. The training involves iterating through the dataset and applying the following steps for each data sample. Take a data sample x0 from the training set. Apply the forward process to obtain a noisy version xt at a randomly chosen time step t. Use the neural network to predict the noise component from xt and the time step t. Calculate the loss using the difference between the predicted noise and the actual noise. Update the neural network parameters using backpropagation to minimize the loss. Sampling is the process of generating new data from the learned model. Starting from random noise, the reverse diffusion process is applied iteratively to transform the noise into a sample from the data distribution. This involves drawing samples from the learned reverse distributions at each step. One of the most used neural network model for image diffusion is the ANET model that allows to generate images of the same size of the input image. We will now go through a notebook to learn how to train a diffusion model from scratch. For this notebook, it is highly suggested to use a GPU since training a diffusion model is a highly intensive task. Let's import needed libraries for this notebook. In particular, we will use Diffusers library. Diffusers is the go-to library for state-of-the-art pre-trained diffusion models for generating images, audio, and even 3D structures of molecules. We will use the flowers dataset, which contain different types of flowers. Let's do some data augmentation and pre-processing. To run this notebook is highly suggested to run it on GPU, otherwise the training, as well as the inference, will take a huge amount of time. We can print some values related to our dataset and display some of the images inside a specific batch. For the training, we will have to define the scheduler, which defines the random noise that need to be added for a specific timestamp. This can be achieved by instantiating a DDPM scheduler object. DDPM is a type of generative model used for generating data, such as images, and the scheduler is responsible for handling the diffusion process over a number of time steps. We can specify some params as number_train_time steps, the number of diffusion steps to train the model. Beta_start, this parameter defines the starting value of the beta parameter, which usually controls the variance of the noise added at each time step during the diffusion process. Here, it starts at 0.001. Beta_end, the final beta value. After that, let's instantiate our .NET model. We have now to train our model. This block of code will take long time even with GPU. Let's outline the main steps of the model. For each step of an epoch, generate random noise. Add random noise to alterate the input sample for a random timestamp. Predict noise from the altered images. Calculate the loss between the predicted noise and the random generated one. Gradient descent. Repeat for other samples. We will then save the model every 5 epochs. At the end of the training, we can plot the loss after each step. We will now upload the model for different epoch by loading the saved weights. We can use the trained model to sample some images from random noise that is similar to the input data. To easily doing that, we can use another class DDPM pipeline by passing as input the model and the scheduler and apply the reverse diffusion process. After 5 epochs, the result is still pretty abstract, but can be improved by using the model trained for more epochs. After 30 epochs, the model starts to produce an image with lower level of noise. We can also play with the number of inference steps. The higher the better the final result. By training longer, the model should learn to produce an image similar to the input distribution. For time purposes, we have limited the training to 200 epochs, but we can improve results by refining the model and by training longer. You will find the weights of the trained model at epoch 200. Before continuing with the next part of the notebook, let's come back one moment to the theory. We have now seen how to train a model and how to use it to generate image from random noise. We will now understand how we can control this process. Diffusion models can be adapted to generate new contents from text prompts through a combination of conditional generation techniques and advanced neural architectures. To generate images, or other data types, from text, the diffusion model must be conditioned on the text. A text encoder, such as a pre-trained transformer model like BERT or CLIP, is used to convert the text prompt into a meaningful vector representation, text embedding. This embedding captures the semantic information of the text. The neural network is modified to incorporate text embeddings. This can be achieved in several ways. If we come back to the previous .NET model, this can be modified to include text prompts in the training process. As already said, this can be achieved by encoding textual information and inputting it at different layers of the neural network. In this video, we will not see how to include the encoding in the train process. We will instead use an already pre-trained model to generate a new image. Let's now come back to the notebook. We can use the Stable Diffusion B14 model. This is a diffusion model that has been trained with techniques similar to the ones seen in the video, but it has also been conditioned on the text. Using it is pretty easy. We just need to import Stable Diffusion pipeline and select the pre-trained model. Let's then move on GPU for faster inference. We can pass a prompt to the model and it will generate some content. In this video, we have learned the high-level details of a diffusion model and how it is trained to generate new images. We have also quickly seen the process of controlling the diffusion process, and we have finally used a state-of-the-art algorithm for creating a new image from text prompt. I hope you have enjoyed this video and see you soon in the next lesson.